switch from MR to ultrasonography. And for those of you guys who don't know me, which are not many in the auditorium, but anyway, I'm a PhD student at the Department of Sports here in Basel, at the University of Basel. And I'm going to jump right away. So maybe we can do a quick show of hands, even if it's Zoom. I'm going to scroll through the people that joined. Who knows the company that is associated with this logo? Just do the hand raise thingy in Zoom if possible. Or if you have the camera on, you can also raise your hand. It's fine. Alrighty. So, okay, this is the logo of a company that's called Hugging Face. I see a couple of you are familiar with it. Hugging Face kind of transformed the machine learning community in a way that it allowed people to share their trained models, to share some of the data sets, and also build spaces where people can use the models. They hosted some challenges on how to best train an algorithm. And basically, by open sourcing this development to the community and not monopolizing it as a company, they accelerated the innovation very, very much. And this is their mission statement. You can read it for yourself for a moment. And this is something that in the machine learning community is quite present. However, in many research communities, we don't have that. And the same is the case for our community in the fields of muscle physiology and biomechanics. So we, at some point, since we thought, okay, we have images and we need to analyze them at some point, and we want to give the community something back and have an innovation here, that we should try and build something like this where we can collaborate, where we can upload analysis models, where we can even share data sets. And this is why, since we identified this as a knowledge gap, we built UMUD, the Universal Musculoskeletal Ultrasound Database. Some of our collaborators are listed here. And it was an effort that started about 1.5 years ago where we had the idea and we slowly built it up. We recently published a preprint. There is a QR code in the presentation later. So I think from where we started to where we are now, we just made some real progress. But since we heard a lot about MR before, maybe some of you might not be familiar why we apply ultrasonography to muscles, and especially in the context of biomechanics and muscle physiology. So I'm going to walk you through a short example. This is an ultrasonography scan that was taken in a similar way as if you would take a panoramic scan of mountains with your smartphone. So you slide the ultrasound probe across the leg in this example. And you can see that there are two areas highlighted. So these are two different muscles. It doesn't really matter what muscles it is. It's just leg muscles. But you can see that on this image, we can analyze the area of the muscles. So we know at this given point on the leg how large a muscle is. Now, say we rotate the probe, so the ultrasound probe, by 90 degrees, we will then get this image. And this is what's called the muscle geometry or muscle architecture sometimes. And there are three features in it. So you can see the bright yellow line that runs through the image here. This is a muscle fascicle. So these are actually the structures that when you walk or jump or exert any force, they contract in your muscle. And these are then the elements that produce the force and you can move. You can see also the triangle that is green. That's what's called a pennation angle. This is the angle of insertion of the fascicles into the lower aponeurosis of the muscle, or the muscle border, which is here highlighted in blue. This is just basically the steepness of the orientation of the fascicles. There are some importance indications to that, but that runs too deep and we won't go into that. And the last parameter is the muscle thickness, which is indicated by the red arrow. So just the two-dimensional distance between the upper and the lower muscle border. Okay, it's nice to have these images. They look fancy at some point, but we also know that these parameters are related to performance. I mean, it seems quite obvious, right? The bigger your muscle is, for example, the more force you can exert. But also this gives us an indication of the muscle quality, let's say, so how much force per area muscle you can exert. And this changes over development in youth, but also if you get older. So from these images, we can infer actually parameters that are related to your physical performance, but sometimes also to your health status. However, so far we've been just talking about 2 dimensions. Generally, what's better is 3-dimensional representation of muscle. And you might know this from MR, that we can assess the muscle volume, but it's also possible with ultrasonography. So this here is a 3-dimensional scan that was done with ultrasonography. You track the ultrasound probe in space, and you get a muscle volume representation here, which means that you can, by stitching 2D images together, you can then get a representation. And this has much more meaning than just 2-dimensional images. So far, we've just been looking at static conditions, but the last option that we also have with ultrasonography is looking at the actual muscle contractility. So here you can see a muscle contracting. You might recognize that there are the fascicles and the 2 aponeuroses of the muscle. And by looking at these videos, when we, for example, walk or exert a force, or in this case, just raise our heels, we can then infer on how fast the fascicles are contracting and how much. And this is related to the amount of a certain force that we can exert in a given time, which then also translate to important health parameters. So that was just the general background, right? So why do we even do the ultrasound? And I think it's important to understand this for the concept of the Universal Musculoskeletal Database. So how is the database built up? And this is just, I'm going to let you watch the video and I'm going to explain it afterwards. So we have an option of selecting muscles, for example, in our web page. In this case, we select the gastrocnemius medialis. We submit a query on the web app to our database. And then we get the links returned from all of the data sets that are included that contain this specific muscle. Another option is to just have an overview of the database in itself, and then just have a representation of the muscles that are in there. So not querying specifically, but looking at the whole thing all together. And so as you've seen before, the database is built up in the Streamlit web app. That is the front end, and we try to make it as user-friendly as possible. But it's built on 3, or the web app contains 3 main pillars. So the first one is the metadata, then algorithms and benchmarks. Metadata is in a way important because we don't have any images in our database. And this is because with ultrasonography, same as with MR, it's considered clinical data, which is often sensitive and is therefore under strict regulations. So what we decided to do is actually to just make the available data sets, which are not many, findable, and we index them. And so our database just includes metadata from available data sets. The second pillar, the algorithms, is that we list automatic analysis algorithms. I'll get to that later, and the same for the benchmarks. So we try to create some common ground truth for our community. So how does the metadata thing works? So we are heavily relying on community contributions in the future because we need people to, or we want to incentivize people to upload their data on some openly accessible service such as the OSF or Zenodo. And then it's based on JSON schemas. This is just a standard JSON file that we can actually check if the user has inputted the correct values. And then this JSON schema with the certain metadata fields, such as the muscle group, for example, or the device that was acquired, is then registered in our database with all of our data sets, which is a MongoDB database. So fairly simple. We then, via our UMUD, the Streamlit web app, we can query the database as you've just seen in the video, and then we will get a return of all of the data sets that match our query. This is such it's just an example, it's not a complete one, but one of these JSON files that describe a data set. So I think you should be able to see my marker. The data type here, for example, this is a standard key, and here we have a value. We have 3 of these key value pairs. It's fairly flexible what you can do. You can use single strings or lists or even integers. And the important thing is that we can make certain fields required as the one below here. So we make sure that people have to enter, for example, the muscle field, because we absolutely want to know which muscle is contained in the data set. And if this is not the case, then basically the whole entry is invalid. And if we then integrate this with Pydantic, so Pydantic is a Python package that's very, very powerful, and it super nicely interacts with Streamlit, because this looks fairly complicated, and for people that are not familiar with programming, it might be overwhelming. But combining Pydantic and Streamlit, it's super simple. We can go on our web app and go to the contribution section, and then you can just enter it in nicely ordered widgets, and you just have to select the values from dropdowns. And it's validated automatically, and in the end, you can send us the JSON, and we will integrate it in the database. So this was me and my master's students about 3 or 4 months ago when we tried to find the datasets, because as I've said previously, there are not many of them available. And this is a bit tricky because we want to build the database, but so far we only found 12 openly accessible datasets that we can use and that are relevant for our community. So as I said before, we really need community contributions in the future. This is actually the data type distribution that we have so far in the database. You can see the muscles listed on the x-axis and the respective counts on the y-axis. So there are sometimes multiple muscles in the datasets. And we also have the 3 different data types that I've showed you before. So you remember the images from the cross-sectional area and the architecture, the videos from the contracting muscles, and the volumes, which were the 3D reconstructions. Now, to the second part, the algorithms. These are 2 examples of algorithms that we programmed, which is DLTrack and DeepACSA. They are just examples. There are many more. They just fit nicely to the introductions, which is why I mentioned them. So you can see that DLTrack is an algorithm that segments the muscle architecture in images or videos, while DeepACSA segments the cross-sectional area. So again, this is linked to the images that we saw in the introduction. And the reason why we need this, and it's the same for MR, is that manually analyzing these images is very tedious. It takes a lot of time, and it's very subjective because you need a lot of experience in doing it, and it's really hard at the beginning to know where the structures are. So by providing, not just us, but many other people as well, providing these algorithms, we can actually speed up the process and make it more objective. And here are some other examples of algorithms. The issue is that there are many algorithms that do the same thing. Some, for ours, they are special in the way, I mean, special is a bit maybe overstretched, but they use deep neural networks. Others are just standard imaging processing algorithms. But when different algorithms do the same thing, it's sometimes different for people that are not familiar with it to decide, okay, which one is the best algorithm that I should use. So we provided an overview of the different algorithms that are available on the web app to just give people a general guidance of what is needed when. And the next thing that we try to do is we want to build up, which is what I'm going to go into detail in the benchmarks section also, is that we compare these algorithms to one another in sort of their performance measures compared to manual analyses, which is in our field still considered the gold standard, and therefore also give users a ranking of the best algorithm for the features that they want to analyze in the images. So now I've already explained what the benchmarks are, but the benchmarks also, I mean, for example, take the large language models nowadays, right? Whenever any company or private person develops a new language model, they are comparing it to some datasets that are considered benchmarks or standard datasets. And this is something that we in our community don't have yet. So what we've tried to do is we've given data to several experts, I think it's 7 or 8, that analyze data manually for us. And these is, again, cross-sectional area data and architectural images that we've seen before. And by analyzing the images with multiple experts, we hope that we can create, or we think that we created a benchmark data sets that can be used not only for deep learning algorithms, but for any algorithm, and that we can start actually comparing objectively which algorithms might be the best. This benchmarking stuff works in a way that we have a benchmark data set. And as I've said, then we have a manual expert analyses. We have, for example, one algorithm and another algorithm. And we then compare certain performance metrics. Now, it's very hard to be kind of general on these performance metrics because they need to be specialized to a certain field. So for us, it's probably reliability statistics. So just, as I said, comparing it to manual analysis. And then we will have an algorithm ranking and validation. This is something that is not yet implemented in the web app, unfortunately, but we will try to do that in the future with the reason, as I said before, that we want to give people the best guidance as possible. These benchmark datasets can also be used in a trainee training sense, because as I said before, it's very hard at the beginning if you're working with ultrasound to know which structures are where in the image. And by labeling these datasets already at the beginning for people to look at, they get a feeling of, okay, am I analyzing these images correctly or am I completely off, and have an objective means to compare it to. So this, as we've seen the mission of Hugging Face, this is our mission. And I'm going to give you a second to read it. It's kind of a very strong statement, and we can definitely not do it alone. So we hope that by making people in our field aware of the issue that we have, that we can actually try to do this together as a community, and therefore in the end help everybody. So just a couple of words on the future developments that we try to do. So we just had our launch of the first official version. I won't say productive ready, but just the first version that seems to be working. And on one hand, we really hope on community contributions. So people just being aware that the database exists and deciding, okay, I want to make my data publicly available so that everybody can benefit from it. On the other side, we want to continuously expand the database, not just with the data sets that include, but also with the expert standards and the benchmarks data set. And one thing that is very important for me is, or what we really want to try, is to host a community challenge. So for example, maybe you know the Kaggle challenges. They are also some machine learning competitions. And we plan to do something similar for our field. So just give people a set of ultrasonography images and ask them to come up with a good analyzing algorithm. And therefore, in the end, we can again make people's life easier. We want to include some advanced visualization, maybe where you can go a bit deeper into the database and play around with it. And as I said, expand the benchmarks and the algorithm section so that people really have good guidance there. In the end, what we try to do with the project is just to increase the available data that we have and therefore be able at some point also to build better algorithms for the image analysis. We want to establish standards in our field so that we have a common ground truth and a baseline where we can all go further from. And the image analysis algorithms, this is something that clearly needs to be improved in the future. And we hope that we can go to a point where we mostly rely on those algorithms and not on our manual analysis. That's the team. Some of them are already present here in the meeting, and you can scan the barcodes, the QR codes, and go to the web app or the preprint. And we are at the end of the presentation. If you have any questions, feel free to ask.